Welcome back, everybody, to this lecture where we're going to go over the intuition and theory behind AdaBoost, or adaptive boosting. So AdaBoost works by using an ensemble of what is known as weak learners, and then combining them through the use of a weighted sum. And AdaBoost adapts by using previously created weak learners in order to adjust misclassified instances for the next created weak learner. So that's a really interesting idea because instead of developing a bunch of trees in parallel, like you could with random forest, instead, adaptive boosting is developing these trees in series. So you develop one tree and use your learnings from that tree and the data set in order to build the next tree. And we're going to see how that process actually works. That's why it's known as adaptive boosting, because you're adapting based on your findings from the previous tree. So let's clarify this idea of what is a weak learner. A weak model or weak learner or weak estimator is just simply put a model that is too simple to perform well on its own. We can understand this by thinking about a decision tree. So the weakest decision tree possible would be known as a stump, essentially one node and two leaves. And this is the weak learner we're going to be working with adaptive boosting. We're actually going to be able to take a multitude of these weak learners or stumps and build out a very good model by using adaptive boosting. So let's see how this is done. Unlike a single decision tree, which fits to all the data at once, and this is sometimes referred to as fitting the data hard, AdaBoost is going to aggregate those multiple weak learners, allowing the overall ensemble model, that is all the decision trees, that is those stumps, those weak learners, to learn slowly from the features. And what we mean by learn slowly is the fact that you're going to have to build a tree first before being able to build the next one. So let's try to understand how this works from a data perspective. And in fact, we're going to imagine a classification task. Here we have two classes, the red class and the blue class. And there's two features. Let's say they're x1 and x2. And we want to be able to classify this space into red versus blue. So what would a stump classification model look like? Essentially, if you just had a weak learner that is a stump, then you know you're already limited to just one feature. So for example, if we have this stump that can only look at one feature in order to split the data, then if we were to look at x1, we may have split the data like this. And you can see clearly there's misclassifications. Two blue are getting misclassified and one red is getting misclassified. Or perhaps you take a look at the x2 feature, in which case you're still performing misclassifications, one red and two blue here. So what we want to be able to do is be able to build up multiple stumps and then apply a weight to them and try to combine them to be a more powerful model. So the question is, how can we actually combine these stumps and how to improve performance with an ensemble of weak learners? And you keep hearing me use that term because that's really the main idea behind AdaBoost or adaptive boosting, is using an ensemble of weak learners to actually create a much stronger model. And this is sometimes known as meta model or meta learning, since technically boosting is not actually a machine learning algorithm on its own. Instead, it's a way of combining machine learning algorithm results, since technically each stump is the actual machine learning algorithm. Boosting is a way of aggregating all of these together. So you may actually see this referred to as meta learning sometimes. So let's talk about the AdaBoost process. And really, I want to focus on three different ways of understanding AdaBoost here. We're first going to go through the main formulas, and then we're going to walk through the algorithmic steps, and then we'll have a visual walkthrough of the algorithm. And really, don't worry too much if you get lost during the main formulas or algorithmic steps, because it's all going to come together for the visual walkthrough. We just want to make sure that the first time you see the algorithms and formulas is not during the visual walkthrough. So we're going to present those first. So here we have the main formulation for the adaptive boosting process. And we can see here that it's actually quite a simple description where you're going to say that the boosted model, that is f of t of x, is equal to the sum from t is equal to 1 to capital T, where we have then lowercase f of t for some value x. And what does this actually mean? Well, capital T represents the actual number of learners you're going to create. That is those number of weak learners or stump models. And as you actually use adaptive boosting, that's a number you can decide on. So before you actually begin the boosting process, you decide on capital T, and clearly you can perform a grid search to see if 5 weak learners are better than 10 weak learners, etc. You can think of this as being similar to choosing how many trees to put in a random forest. But keep in mind, for adaptive boosting, these trees are going to be built out in series. So when we think about these trees, we're thinking about those weak learners, those stumps, and that is what lowercase f of t of x is representing, where each lowercase f of t is a weak learner that takes an object x as input and then returns a value indicating what it believes the prediction could be. For example, whether it predicts red class or blue class. Now, what do we actually use to define this lowercase f of t of x? In this case, each weak learner is going to produce what is known as an output hypothesis, or h of x. We can think of this hypothesis as just what the stump itself, that weak learner, hypothesizes the output for the classes should be. So it's going to hypothesize that some points should be red and some points should be blue. And then we have this critical component, which is this alpha parameter, or alpha of t. So of t means for that particular weak learner. So this particular tree, t, is going to have some hypothesis, and then it's going to be multiplied by what we can call a weighting factor. So we can imagine if this particular stump is really good at predicting, we would want that alpha parameter to be quite high, because we want to have that stump or weak learner give a lot of input. If a weak learner was not good at predicting in classes, we would want that alpha parameter to be pretty low, because that means that weak learner is not good at producing correct hypothesis predictions. And we end up deciding on this alpha parameter, this coefficient, so that the sum of the training error, that is capital E of t, of the resulting t-stage boost classifier is minimized. And this is essentially just a fancy formulation for the error term that we're actually trying to minimize in order to calculate the correct coefficient to multiply that hypothesis by for the weak learner. So these are the main formulas we're going to keep in mind as we do a walkthrough of the adaptive boosting process. And keep in mind, the other thing that's going to be occurring is not just this coefficient being multiplied by the hypothesis or the weak learner, but what we're also going to be doing is updating a set of weights that is attached to each of those points. So you're going to see this wi of t, where I just stands for the index of the particular data point in the row, and t stands for the particular weighting for that particular tree. So we have these trees, that is capital T trees, and we're going to keep cycling through these, which means we're going to have that alpha coefficient for every single weak learner. And then for every single weak learner, we're going to have an individual set of weights that gets applied to every single data point as training continues. So now let's talk about the algorithm steps. What we're going to do is we're going to start off with some number of samples. So we have data point x1, data point x2, x3, etc. So these are just essentially the number of circles you have inside of your feature space. In this case, you can see I have 5 red points and 5 blue points, so n would be equal to 10 in this particular case. So I have 10 samples here, x1, x2, x3, and so on. And then keep in mind, for this particular case, we want binary classification, so I have some set of desired outputs. I'm going to want to output a prediction, y1, y2, y3, and so on. And my predictions are going to be in the range from -1 to 1. And you'll soon realize that we're going to be using these as almost a probability of belonging to each class. And then what we're going to be doing is we set up initial weights to every single data point. So we have w of 1, 1, where the first one represents the actual data row that weight is being applied to, and then the second one represents the fact that we're setting this up for the very first learner, where t is equal to 1. And what we're going to do is set up the initial weights to be equal to 1 over n. And let's think about that. If we were to have 10 data points, that means we would set each data row to be 1 over 10, essentially saying that at the very start of the algorithmic process, every single data point has the same weight attached to it, 1 over n. then what we're going to do is we'll move on to calculating this error function that we showed earlier, and then using that, we're going to be able to figure out a coefficient later on down the line. And keep in mind that the weak learners themselves are going to output some hypothesis given that x data point that is in the range from -1 to 1. So how does the actual training occur? This is kind of our setup process. During training, what we're going to do is for t in 1 all the way to capital T is how many weak learners we actually decide to create, we're going to choose a hypothesis of x that is just the weak learner, and we're going to find a weak learner that minimizes the error term such that it fits these conditions, and you can see the actual formulation for that alpha coefficient, where it's equal to 1/2 the natural log of 1 minus this sigma or error term over that error term for that tree. Now, don't worry too much about these formulas right now. You're going to see how it all plays out when we do a visual walkthrough of the algorithm. But hopefully you can now get an idea that all we're going to be doing is for every single one of these trees, we're going to end up figuring out what is the appropriate coefficient in order to figure out the minimization of that error. And the other thing to keep in mind is we're doing this for all the trees. So for all the trees, as we build them out in series, we're going to end up choosing the hypothesis, and then we're going to try to find something that minimizes this term, and then we're going to end up choosing that alpha coefficient. So what's the next step after that? Once we've done that, we end up adding it to our existing ensemble. So we have the set of learners already created that we call capital F of t minus 1. So that's all the set of weak learners that have been already created, and then we're going to add on this coefficient times the hypothesis of this weak learner. And then for the next weak learner, we update all the weights, and those are the weights that are actually attached to each of the data points. And keep in mind, we keep renormalizing the weights so that the sum of all the weights is equal to 1. So add them to the ensemble, and then update the weights. And then those updated weights are going to be used by the next weak learner. So let's actually visualize this process. And this is where things will hopefully become very clear. So now that we understand the basic formulas we're using, let's see them in action. So remember, we have our setup here ready to go. And now it's time to choose this hypothesis, that is that weak learner. So we decide that on that data set, we have this very first weak learner. It chooses x1, and it does some sort of division of the data set, and it's going to end up classifying those particular points. And then what we're going to do is we're going to add the weighting to the points, and we're going to weigh the points that it misclassified heavier than the other points. And I'm representing that here by the size of the points. So notice here that this particular model is going to misclassify 3 red points. So I'm going to add a stronger weight to those points and then reduce the weight to the points that it got correct. And then once I've done that, I'm going to end up choosing that alpha coefficient to order to multiply that by the weak learner. And that's my very first tree. But keep in mind, this is a process that is built out in series. And what I have now to move on to the next tree is the updated set of weights. So what I'm going to do is take that updated set of weights, here represented again by the size of the circles, and now I'm going to have another weak model. But this weak model is not learning on the original data set. It is now being trained off this data set that has these weights attached. And this is why we're saying that the model is learning slowly, because it doesn't fit the data hard, so to speak, where it takes in all the data at once. Instead, it's using the learnings from the previous weak learner to say, hey, maybe take a look at these points more critically because I'm attaching more weight to them. Which means you're going to have another weak learner that very likely may have to choose a different feature, for example, x2, in order to try to classify this given more weight is being added to those particular points. So it's really trying to get those heavier weighted points correct. And so maybe you end up with this classification. We go through the error term calculation in order to figure out, again, that coefficient. And notice here I have my first tree, tree t, and it has its own coefficient, coefficient of t, and then I have my next weak learner, or that next dump, and that's going to have its own coefficient, coefficient at t plus 1, multiplied by the results of this model. And then what we're going to end up doing is we're going to update the weights again. So take a note, what did that weak learner get right and what did it get wrong, and adjust the weights accordingly. So now we have these 2 points that we need to make sure we classify correctly. And not every weak learner model is going to be able to perform perfectly, but it's going to be able to use what other previous stumps learn for the next data set. So then we update the weights again, and then some other weak learner model is going to come in and try its best, and it's really going to want to classify those more weighted terms or more weighted data rows correctly. So again here, maybe we get some misclassifications again, and keep in mind it can be allowed to misclassify those heavy weighted points. It's less and less likely that it misclassifies those because it keeps adding weight to them, but that doesn't mean it's impossible for it to misclassify. But then that model ends up receiving its own coefficient term, and we continue this process for capital T amount of trees. And so recall the original formula here for boosting, where each of these lowercase f of t trees themselves is a weak learner. And all it is that coefficient multiplied by the hypothesis or the output hypothesis that the weak learner produces for each sample in the training set. Which means we actually end up summing all of these predictions together. So given that we have these various weak learners, and they each have their own unique coefficient, we're going to be able to actually create something that's going to appear like a blended model or an ensemble of all these weak learners. Which means when you actually perform AdaBoost and just get to see the final result, you would be able to see something that appears to be a meta-learning. It's taking these multiple weak learners, that is the simple stumps, and then it's going to multiply them by the coefficients that it's being solved for with that error term, and that will hopefully then build out a very strong model. And so we're going to take an ensemble of weak learners in order to build a strong learner. And this is the adaptive boosting process. Adaptive boosting because you end up adapting due to the learnings of the previous trees. So let's have a little quick review. AdaBoost or adaptive boosting uses an ensemble of weak learners that learn slowly in series. Then, certain weak learners are going to end up having more say in the final output than others due to the fact that they're being multiplied by that alpha coefficient or alpha parameter. So for some models, that is stumps, that are not very good at predicting the final y output, then we can imagine that alpha coefficient is going to be very small. But for the stumps that are actually pretty good at predicting the output, we'll have the alpha coefficient be larger. And then each subsequent t weak learner is built using a reweighted dataset from the t-1 weak learner. Now let's talk about the intuition of adaptive boosting. We can imagine that each stump essentially represents the strength of a feature to predict. Because in adaptive boosting you almost always just get stumps, that means each little weak learner is really only considering one feature to split, and then it has that alpha coefficient attached to it. So that's really the intuition behind adaptive boosting. You're essentially just figuring out how important is each of these features, and is there a set of coefficients I could use in order to kind of combine everything together to an ensemble to get a strong learner out of these many weak learners. So building these stumps in series and adding in that alpha parameter, really multiplying that alpha coefficient by those weak learners, allows us to intelligently combine the importance of each feature together. And that's really the intuition behind adaptive boosting. How important is each feature, and slowly learn this as you build out those weak learners. Now, some notes on adaptive boosting that I want to mention. Unlike random forest, it is actually possible to overfit with AdaBoost. However, it does take many trees to do this. And as you build out more and more trees, that is increase that capital T number of how many weak learners you're trying to produce, usually your error is going to stabilize. Recall that with random forest, eventually your error term stabilized no matter how many trees you added to it. You'll get a very similar behavior for adaptive boosting, where even if you keep trying to add more trees, you're not really going to decrease your error. However, if you try to push way beyond that, you will eventually produce an overfitting model. So keep in mind that it is possible to overfit, but usually you're not going to hit that because you're not going to see that improvement in performance until you go way beyond what's necessary. Okay, let's go ahead and move on to seeing adaptive boost or AdaBoost in practice. I'll see you at the next lecture.